when we started this lesson, we talked about that the big theme here is things that come in threes to do with energy and the earth. Okay? And we said yesterday, the first thing we talked about was the three fates of light. Okay? So three fates of light. Okay? When light encounters the earth, one of three, or actually more than one, but okay, three things can happen to it. It can be absorbed. Okay, so if it's absorbed, okay, then that means energy is gained. That's a weird beat. Obviously I can't spell this morning. Oh, okay, so it could be absorbed. I still can't spell that this morning. Man, it is tough today spelling English. It's tough today. Absorbed. Absorb it. There we go. Okay. And it can be reflected. Okay. And it can be converted. Okay. So it's important to know that if plants are present, that one happens. Okay. If plants are present, then there's going to be conversion by photosynthesis. That doesn't mean the other two don't happen. Right? There can still be some reflection and there can still be some absorption. It is never an all or none situation. Okay? There are going to be areas that are darker and areas that are lighter. Okay? The darker areas have a lower albedo. Okay? Super important word. That's going to come up all the time. Okay? They will have a lower albedo, okay, and they will absorb more energy. The thing we talked about yesterday was all the ash from the forest fires that was falling on the glaciers, lowering their albedo, okay, and causing them to melt more because they were absorbing more solar energy. Okay? If the ice is perfectly white and pristine, then it reflects away a lot of the energy, okay, and not a lot of energy would be absorbed. Okay? Everyone follow on that? Okay. So those are the three fates of light. Okay. The other thing, okay, are the three parts of the earth. So you can see that's the first point here. Okay. The three parts of the earth are the atmosphere, okay, the hydrosphere, and the lithosphere. Okay. These are all in the notes later. Don't worry about scrambling those ones down. Okay, but they all have a role to play in how they absorb, okay, reflect, or convert, okay, the sun's energy. They also have a role to play in the transfer of energy from one place to another. Obviously, the equator gets more energy than anywhere else. That energy has to move from the equator to the poles because of the second law of thermodynamics. Okay, and the last set of three things are the three ways heat, or thermal energy, is transferred from one place to another. That is by conduction, convection, and radiation. Okay, so energy can be transferred from one place to another by those three methods. Right, and we will talk about those. So these things are all going to be tied together in this lesson about energy, energy transfers, and what happens to the energy. Okay, so if it's absorbed, then it can be transferred. Okay, and it can be transferred by conduction, convection, or radiation. Okay, what parts of the Earth, atmosphere, hydrosphere, or lithosphere, are the most responsible for moving energy around? What role do they play? Okay, there's going to be a lot of tying these things together, okay, throughout the lesson today. Right? But those are the triad of threes. Okay, the three sets of three things, okay, that are going to be tied together today. Okay, you do not need to know this diagram. Okay, I am never going to ask you about the layers of the atmosphere. Okay, just so we're clear, I'm never going to ask you about that. Okay, we live in the lowest layer. Okay, that is the troposphere. Right, that is where the bulk of our weather happens. It's where the bulk of the energy transfers are occurring. Okay? The other layers of the Earth's atmosphere don't really have much of a role to play in any of that because, well, nothing lives up there. Okay? In fact, there's only a few places on Earth you can stand where you would actually be outside of the troposphere. Okay? You would actually be a little bit in the bottom of the stratosphere if you stood on any of the world's tallest mountains. Okay? So Everest, K2, okay, those kind of places are actually a little bit up into the stratosphere. Right? It's why when you're at the top of those mountains, you're in a scary sounding place called the... Oh, nobody's heard this term before? On the top of those mountains, you are in what's called the death zone. Okay? The reason for that? You're slowly dying. Okay? If you are up above the troposphere, your body cannot live long term up there. Okay? Even sleeping at that altitude, you are slowly dying. Okay? Your body just cannot adapt to the low pressure, okay, of the atmosphere, the low oxygen content, all of that kind of stuff. It's why climbers die on the tops of those mountains. They just get really, really tired, and they just sit down and go, I'm going to rest, and they never wake up. Okay? You guys ever seen any of that stuff on the top of Everest? Like, they actually use the bodies of dead climbers as markers. Okay, so, oh, I'm halfway to the top because there's green boots. I kid you not. Yeah, okay, it's morbid. Okay, so if you get above there, there isn't enough air. There isn't enough air to really do much, so there's not a lot of energy transfers or things like that going on above the troposphere. So we're going to be mostly concerned with what goes on here. Tops of our, like, thunderstorms, thunderhead clouds, they could go up into the stratosphere a little bit. That's usually where you see them flattening. Okay, at the top, if you ever see those thunderheads start to get flat and spread out at the top, okay, they're up into that area. Okay, so the big role of the atmosphere is this. It's super fluid. Okay, gases are a fluid, but they flow way more easily than liquids do. That allows the atmosphere to do a lot of energy transfer.
Where would you be if you were on an airplane?
On an airplane, you would be just above the troposphere, 26 to 30,000 feet. Yeah, it's just kind of on the borderline. Okay, they actually say that when you're on top of Mount Everest, if you time it right, you can actually see passenger planes fly by below you. Okay, because they don't go over the top. Okay, so if you're looking at what the role of the atmosphere is, it is to transfer thermal energy. Okay, that's what wind is. Okay, wind is evidence that there are differences in temperature and pressure, and it's moving to equalize because nature always wants equilibrium. Okay, so there's going to be a lot of movement of air. Okay, that's convection, by the way. Okay, one of those other big three things that we were talking about. Okay, the atmosphere has the biggest role to play in transferring thermal energy because it can move the most, and because it's in contact with all parts of the Earth. Okay, the ocean's not in contact with all parts of the Earth, but the atmosphere is. Okay, so it has the biggest role to play in moving energy from the equator to the poles. Okay, questions there? Okay, so the atmosphere, okay, has this big role in maintaining the Earth's temperature. Okay, it has a greenhouse effect, which gets a bad rap, but is actually a sort of a good thing as long as it doesn't get out of control. Okay, without the greenhouse effect, Earth would be a frozen snowball. Okay, so we do need a little bit of greenhouse effect because it does help to trap the heat and to make it livable here. Obviously, we don't want it to get out of control or we'll turn into Venus, and that's bad. Okay, so when the solar energy comes in, okay, it's going to do a bunch of things. We said it could reflect, it could be absorbed, or it could be converted. Okay, so there's actually a number of things that happen when that solar energy comes in. One of the first things is the nature of our atmosphere causes some of the light to be back scattered. Okay, that means instead of traveling in straight lines, okay, it gets kind of thrown in all directions. Right? The wavelength of light that does that the most is blue. That's why the sky is blue. Okay? The sky is blue because blue colored light gets back scattered, thrown everywhere by the gas makeup of our atmosphere. Okay, so it gets back scattered. So the sky is blue because it scatters blue light. You've probably been told somewhere along the way that the sky is blue because it reflects the ocean. That's not true. What color is water? It's clear. The ocean is blue because it reflects the sky. Have you ever noticed on a cloudy day the ocean's not blue? It's gray. Okay? So the ocean is blue because it reflects the sky, not the other way around. Okay? The sky is blue because it scatters blue light. Okay? When light gets scattered, some of its energy is lost. That slightly warms the atmosphere. Okay? Tops of clouds, are they quite white? Does white have a high albedo? Then that's going to reflect. Okay? If it's a cloudy day, it's cooler. Why is it cooler? Because the tops of the clouds are reflecting a whole bunch of the light back into space. Okay? So it's not getting to the Earth's surface, it's not being absorbed, it's not raising the temperature. Okay? Now, some of that stuff is going to get all the way to the ground. Okay? When it does, some of it will be absorbed. That'll be based on what color is the part of the Earth it's hitting. Is it dark? Is it light? How much of it gets absorbed? How much of it gets reflected? Okay? Some of that stuff will be reflected onto the Earth, and it'll go back out into space. Some of it will get trapped by the greenhouse gases, and it'll come back. That gives it a second chance to be absorbed. That's the warming effect of the greenhouse effect. It gives all of that solar radiation a second, maybe even third opportunity to be absorbed by the Earth instead of reflected. All right? Making some sense there? Okay. Let's leave it at that. We'll head over to the church here. Okay? And then we'll come back and talk about albedo when we come back. All right, so we were just talking about what happens to the light when it comes in and it hits first the Earth's atmosphere. Okay, we said some of it gets backscattered. The blue light gets backscattered. That's why the sky is blue. Okay, some of it gets reflected by clouds. Right, some of it's absorbed by water vapor, gases, things like that. Okay, that would warm up the atmosphere, obviously. Okay, then some of it is going to get all the way to the Earth's surface. That's going to be either absorbed or reflected based on the albedo. Okay, that key word there, the reflectivity of the Earth's surface. The higher the albedo, the more reflective it is. Okay, if it gets absorbed, then the story is over. The temperature is going to go up. If it gets reflected, it might get all the way back out to space. It might reflect back down to the Earth off of greenhouse gases and things like that. Okay, so this is what we're looking at. The two seasons, because I mean in Alberta we have summer and construction, right? Or winter and construction season. So right now, we're in construction season, or summer, okay, where we have darker colors exposed to the sun. All right, so those darker colors have a lower albedo. So that means that light that comes in from the sun, 70% of it is being absorbed. Okay, now some of that 70% is also being converted, but we would count that as absorption because that is increasing the energy of the Earth in that place. Right? It's not thermal energy, but it's chemical energy, so it's being absorbed. Okay? 10% would be reflected off of oceans, okay, or lakes or whatever, okay? And 20% would be reflected off of light-colored surfaces. Maybe you got light-colored rocks or something like that, okay, that are going to reflect. But 70% of the incoming radiation in the summertime is staying put, right? The opposite, and even beyond the opposite of that, is true in the wintertime. When it's covered in snow.
Wait, so if it's a darker color, does it have less albedo?
Yes, lower albedo is reflectivity. So the higher it is, the more reflective it is. Okay, so in the summer or in the wintertime, the albedo is much higher. Okay, we're covered in white snow, and 85 to 90% of the incoming radiation reflects back. Okay, it does not get absorbed. The only stuff that gets absorbed would be off of maybe an exposed dark colored rock, okay, or maybe an exposed tree, okay, or something like that that's sticking out. That could be absorbed. Okay, it's also why typically if you've got maybe a big rock in your yard, the snow around it melts first. Okay, it's going to be able to absorb more solar energy because it's darker in color. It sticks out above the snow, okay, and it's going to get hotter, so the snow around it will melt faster. Okay? We also talked about how yesterday in the wintertime, when we get snow, we throw sand and salt on the roads. Okay? The sand lowers the albedo and allows more energy to be absorbed. The salt lowers the melting point of the snow. Lowers the melting point of the snow, so it melts more quickly. Okay? So those two things kind of work in concert to help us get rid of the snow. Okay? Making some sense there? Okay, so lots of practical applications of albedo. Okay, so when the atmosphere is working, right, the gases that are present there do have an effect on climate. Okay, the amount of oxygen, nitrogen, carbon dioxide, all of that affects how much energy is able to come in, how much gets scattered, how much gets reflected off, how much gets trapped by greenhouse gases like carbon dioxide, CFCs, methane. Where does methane come from? Farts. Comes from farts. True story. Okay, feedlots actually produce a whole bunch, okay, of methane. The cows produce a lot of methane, pigs too. Okay, also there's lots of bacteria that produce methane as a byproduct. Okay, it is a greenhouse gas, but it is combustible as well. Yes, that means you can light your farts on fire. Technically, practically, it's quite difficult. Apparently, I've never tried because that's weird. Okay, ozone, nitrous oxide. Okay, all of those things are going to help trap, okay, the heat in, okay, acting as greenhouse gases, which is what you see in that diagram there. Okay. All right. This diagram actually has nothing to do with this slide, but I found it the other day and I wanted to show it to you. Remember when we talked about the rain shadow effect the other day? Okay, how when moist air gets pushed up over a mountain, all the moisture falls out on one side. Okay, this is Mount Robson. Okay, and this is actually this happens all the time around Mount Robson. I never got a picture of it when I was there, but you get moist air coming in, and the mountain is so tall that when it has to go up and over, there's not a cloud in the sky, and then all of a sudden, the top of the mountain is shrouded in cloud, and then the cloud is gone, and there's a fresh bit of snow on top of the mountain. Okay, if that moist air gets pushed up and over, it gets cold enough that all that stuff just falls out on the top of the mountain. So it could be a perfectly clear day, and then all of a sudden a cloud will appear around the top as a moist air mass tries to move up and over. Okay, so that's that rain shadow effect. All right, so the hydrosphere, okay, is all the water on Earth. Okay, so atmosphere, biggest role to play in transferring energy, pretty big role to play in absorbing energy. Okay, the hydrosphere works in concert, okay, with the atmosphere through the water cycle. Okay, because water can obviously be a liquid, a solid, or a gas on Earth. It exists in all three states. Okay, what's important about that is that within the water cycle, there are changes in energy. Ice is obviously the lowest form of energy for water. Steam or water vapor is the highest form of energy for water. Okay? So the water cycle actually helps us to move energy from one place to another through different states of water. Okay? So if we're looking at all the water on Earth, okay, 97% of the Earth's water is in the oceans. Okay? 97% of it is saline. Okay? That means salty, so we can't drink it. Right? 3% of it is fresh. Okay, that's obviously a very important resource worldwide for people, okay, for drinking water, etc. Okay, of that 3%, if we break that up, 2/3, actually more than 2/3, is ice caps and glaciers. So in its solid form, okay, 30% of it is groundwater, and believe it or not, lakes and rivers only account for about 1.2% of all the water on Earth. Okay. Okay. Making sense there? We got to talk about the water cycle here and where all the energy comes in. Okay, so if you don't have the notes package with you, I want you to just quickly diagram the water cycle here. Okay, put in the different steps there. So you got your transpiration, evaporation. Okay, you've got runoff. Okay, you've got condensation, precipitation. Okay, actually we'll just write condensation on there because it's actually not in the diagram. The writing on the diagram is kind of hard to read. Okay, so the big steps you need to have on your diagram are evaporation, transpiration, that's evaporation from plants, okay, condensation, precipitation, okay, infiltration, and runoff. Okay, those are going to be the main processes that I'm going to be concerned with. Okay? And this is not necessarily about, can you label the water cycle? Because I know you can. You've been learning the water cycle almost every year in science, your whole academic career. Okay? One more time. But this time we're looking at it from an energy standpoint. Which one's giving you trouble?
The one like, the one below it.
Here?
The one beside
This
it.
one?
Yeah.
Runoff. Runoff. Which one?
Is that infiltration?
Infiltration, yeah. Okay, so as I was saying, our big concern with the water cycle here is where's the energy in the water cycle? How does the water cycle help us to transfer energy from one place to another? Okay, so yes, we need to know the processes, but we need to know where does the energy go in, where does the energy come out of the water cycle? Okay, now, in order to evaporate water, either directly from an ocean or a lake or a river, okay, or a puddle, or off of a plant when it's carrying out photosynthesis. Okay, those two processes, transpiration, okay, and evaporation, are both energy in. Okay, that is energy being absorbed and turned into another form. It is changing liquid water to a gas. Okay. Now, which do you suppose is easier to move? Liquid water or water vapor? Which is easier to move? Water vapor, yeah. Okay. As a gas, water is really easy to move. That's what weather is. Okay. Weather is the movement of air. And sometimes that air contains huge amounts of water vapor. Okay. Here's what we have to understand about water vapor and it being a way to transport energy. For every gram of liquid water that turns into a gas, okay, we are looking at over 2,000 joules of energy being transported in that 1 gram of water vapor. Okay, it is huge in terms of the amount of energy that can be reserved or stored in a storm cloud. Okay, every gram of water represents over 2,000 joules of energy. Okay, so imagine how many grams of water would be in a storm cloud. Okay, and when we get a thunderstorm and all that water comes up, it's running in the gutters and things like that. Okay, every gram of water that's there on the ground that came out of that cloud released 2,000 joules of heat when it condensed back into a liquid. Okay, everyone with me there? So we're talking an unfathomable amount of energy being moved by water vapor through the water cycle. Okay, because we don't have a lot of liquid water on the ground around here. Okay, anything that evaporates from here is most likely evaporating from grasses and things like that. So most of the water vapor that we get coming here came from somewhere else, which also means it carried energy that was absorbed from somewhere else, and it's bringing it to us. Okay, so this water vapor, okay, transports latent heat. Okay, that is a term we're going to use a lot in this unit. Okay, latent heat. It is the energy that is stored in water vapor. Okay, now that water vapor goes somewhere else. Let's say it evaporated off the Pacific Ocean, it made it over the mountains, and it's coming to us. Okay, has that energy moved a long way? It has, okay? It's come from somewhere else to us. That's a transport of energy through both the hydrosphere and the atmosphere, okay? The water came from the hydrosphere, but to move it required atmospheric movement or wind to transport it here, okay? When that stuff condenses, it releases thermal energy. So condensation, okay, is energy out. Okay, so all that energy that the water vapor had stored, okay, that had gained by being evaporated into water vapor, okay, comes to a different spot, and when it condenses back into a liquid, it releases all of that energy. Okay, so that's some thermal energy. Does the liquid water, when it falls on the Earth's surface, also have some mechanical energy? It does. Okay? That mechanical energy also came from it being evaporated from somewhere else. That was all solar driven. Okay? So when we're looking at runoff, runoff is also energy out. It's why we can build hydroelectric dams and use them to generate electricity. Okay? Hydroelectric dams generate electricity using solar power, believe it or not. Okay? The water that is turning those turbines only has its energy because it evaporated from somewhere else, was transported here, fell as rain, got in a river, and ran downhill. Okay? But the only way it got to that point in the first place was because of the sun. Okay? When it comes right down to it, everything on Earth is solar powered. Okay? Even my old V8 truck, okay, which I love telling people. I love telling them it's solar powered if they get on me about driving a gas guzzling vehicle. Okay? I tell them, chill. It's solar powered. And they're like, whatever, you fill it up with gas. I'm like, yeah, well, where do you think the energy from the gas came from? The gas I put in my truck was plants 500 million years ago. They carried out photosynthesis. Then they got fossilized, pressure, all that kind of stuff turned into gasoline. Solar powered truck. Get off my back. Okay? It's not a lie. It's totally true. That energy came from the sun 500 million years ago. I can't help that it needed to wait a while for me to use it. It's not my fault. Okay? So everything that we use, including hydroelectric power, still is energy from the sun. Okay? It's just kind of gotten there by a roundabout route. Okay. Now, infiltration, okay, that's not so much an energy process, but it can store energy, okay, in the form of liquid water underground, okay, which can be harnessed later if there's any pressure from below that pushes it back out. Okay, so we've got energy in, transpiration and evaporation, okay, condensation and runoff represent energy coming back out. Okay, even these glaciers still represent some energy. Okay? Glaciers are usually pretty high up on mountains where the water would have a lot of potential energy. When it melts, it's going to run off. Okay? It's all energy and it's all from the sun at some point. Okay? Everyone with me there? All right, so if I ask you a water cycle question, yes, you need to know transpiration, evaporation, condensation, precipitation, and runoff. You need to know those processes. Okay? But you need to know where's the energy going into the cycle, where's it going out of the cycle, and how does it transport that energy. Okay? The water vapor moves it from one place to another. Okay? And the runoff moves it back. Okay. All right, questions on the water cycle and energy? Okay, we already talked about that one. Okay. All right, the lithosphere. Okay, litho means stone. Okay, the prefix litho means stone. Okay, so we are now talking about the solid part of the earth, the rocky part of the earth. Okay, this part has the least amount of involvement in transporting energy because, well, the solid part of the earth doesn't move very much. Okay, so it's not like energy absorbed in the ground at the equator is going to move through the Earth's crust to us. Okay, so the lithosphere has basically zero role in transferring energy. It has a massive role in absorption. Okay, because this is where the albedo is, right? The sun's light hits the Earth's surface and it's either reflected or absorbed, okay, based on the albedo of the lithosphere at that particular place. It is also where plants grow. Okay, they grow in the dirt. Okay, I mean, there's also plants in the ocean for sure. There's algae, but we're talking about the crustal part of the Earth here. That's where plants grow, and they're the things that can convert solar energy into chemical energy and support food chains and environments and things like that. Okay, so that's the role the lithosphere plays. Okay, the lithosphere supports absorption and conversion by providing soil for plants. Okay, so soil, topmost layer of the Earth's surface. Is soil the same everywhere? Absolutely not. You'd be surprised what counts as soil in some places. We're pretty fortunate here. Okay, we have pretty good soil. It's pretty sandy, but it's pretty good. Okay, that's why we can grow so much food here. Why agriculture is such a big thing, and forestry, for that matter, also such a big thing, because we have good soil here. There's lots of places that would love to have the quality of soil that we have. Okay, like for example, if you went to Arizona, okay, they have soil in Arizona. Doesn't look like soil though, does it? But it's still the topmost layer. It's just kind of rocky and dry, right? Not really good for supporting a lot of plants, right? So soil is its own ecosystem, okay? It has both biotic, living, and abiotic, non-living parts, okay, that all kind of work together to support the growth of plants. Okay, how many people have ever dug a hole in their life? Okay, if your hand is not up, at some point get a shovel and dig a hole, because you got to experience that, it's awesome. Okay, now, when you dig a hole, do you ever notice that the dirt's not the same all the way to the bottom, provided you actually dug it like a significant hole? The soil's not the same all the way down. Okay, so you got like the dirt, the soil part, the topsoil, then what's underneath that? Clay, yeah. There's usually clay underneath that. And if you dug far enough, actually, you don't have to dig very far. Okay, you got soil, clay, and then what's underneath that? Clang. Rock, yeah. In Okotoks, you don't have to dig very far. We're on like this massive outcropping of sandstone here in Okotoks. Okay, in our house that we were in before the one we're in now. Okay, we were trying to build our fence. We brought in a bobcat to dig the holes for the fence posts, and there were 2 holes that ended up being this deep. Okay, less than a foot deep, because he hit the bedrock. Okay, and he couldn't dig any further. Okay, I threw a pick at it. You couldn't break it up. It was just a big giant chunk. When they dug the hole for our house for the basement, they pulled out chunks of sandstone the size of a Volkswagen, okay, out of the hole. It was just the outcropping of sandstone here is very close to the surface in this town. So you've got your topsoil. That's the part that plants grow in, obviously. Underneath that is a layer of clay, and then underneath that is what we call the parent material, or the bedrock. Okay, now. It doesn't matter where you go. There's always going to be clay underneath the topsoil. Okay? Even if you had a sandbox as a kid, there's probably clay underneath the sand. Okay? Now, having built the sandbox for my own kids, I know I didn't put clay in the sandbox. But after 5 years, there was clay underneath the sand. How does it get there? Always clay underneath. Okay, I didn't expect anyone to know the answer. Okay, so here's the thing about clay. The particles that make up clay are very fine. Okay, like if you had dry clay and you kind of rubbed it between your fingers like I'm demonstrating right now, it would feel like flour, like almost slippery. Okay, you don't feel the individual grains. Okay, if you pick up topsoil and do that, you can feel the grains, you can feel grit, okay, like especially around here where our topsoil has so much sand in it, okay, you can feel the grains, the grittiness between your fingers. Clay feels very, very fine. So the reason clay builds up underneath is that's the really fine stuff. it's actually dust that's settled. And then when it rains, it washes it down between the larger grains of the topsoil. So it collects and builds up underneath. Okay? That's why my kid's sandbox that I put no clay in, after 5 years, had a little layer of clay on the top. Okay? All that dust and all that really fine stuff that just settles down, washes in when it rains and collects underneath, because it's small enough to go between the larger grains above it. Okay? Everyone kind of following me there? Now, here's the thing about clay. Clay holds onto moisture really, really well. Okay? It doesn't let it go. That's why it can get kind of hard and difficult to dig through. It's almost like cement. It just holds itself together. All right? So when you dig a hole, you are going to see the different horizons of the soil. Okay? We are going to be concerned with only 3 horizons. Okay? That is going to be the A horizon, or the topsoil, the B horizon, which is subsoil, that's the clay, and then the C horizon, okay, which is just rock, bedrock, or what we often refer to as parent material. Okay? The reason we call it parent material is it's where the soil came from. Dirt comes from the weathering of rock. Okay? It just wears and little grains fall off of it, and it slowly erodes, okay, weathers. That's what builds up soil, okay, is the weathering of rock. Okay, so A horizon is the topsoil, B horizon is the clay, C horizon is the rock or the parent material. Now, from place to place, that profile looks different. Okay, there are some places, here would be an example, okay, on the prairies, where there's lots and lots of topsoil. Okay, Okotoks is a bad example because we're on an outcropping, but if you go out into the fields out there, okay, the topsoil is quite thick. Okay, the B horizon is actually quite thin, and then underneath that is the rock that all of it came from. Okay, I said earlier that here our soil is really sandy. The reason is the bedrock here, the parent material here, is what kind of rock? Sandstone. Okay, so our soils are naturally going to be sandier because the rock that's eroding to produce it is sandstone. If you go further north, okay, where the bedrock is limestone, the topsoil looks and feels a lot different. Here, our topsoil is kind of a light brown, okay, and it's fairly gritty. If you go up to north of Red Deer, between Red Deer and Edmonton, the soil is black. Okay, it is much, much darker and finer. Okay, and it looks and feels considerably different. I'm not saying you have to go to a bunch of different places and dig a hole. I've done that for you. Okay, but I can tell you for sure that the soil is different from place to place. Okay, so this would be a typical soil profile for our area. Okay, A horizon, topsoil. Okay, around here, that's pretty thick. The reason for that? Every year, the grass here dies and builds up a layer of thatch, which then eventually decomposes and makes more topsoil. Grassland ecosystems generally have thick topsoil because every year the grass grows from the roots. Okay, it doesn't like regrow the blades that were there last year. That stuff has to decompose and grow and just become soil. Okay. Okay, so you can see obviously the different colors here. Okay, so this would be your A horizon, B horizon. That would be the sandstone, okay, parent material down below. How much nutrients would there be in this layer, in the B horizon? Very little. Okay, this is dust and things like that that is washed down below. Okay, not a lot of nutrients. The nutrients are here. This is where stuff is being actively decomposed and the nutrients within it are being released. The topsoil is where it's at in terms of nutrients, okay, and growing medium. Okay, the B horizon is mostly clay. Okay, so you can go to some places and there's almost no A horizon at all. It's just everything grows right out of the clay. Tropical rainforest is a prime example of this, and that might seem counterintuitive. Okay, a giant, thick, luxuriant tropical rainforest has almost no topsoil. Okay, everything grows directly out of the clay. Okay, because clay cements itself together and it's not washed away easily. But topsoil is loose. Okay, it's generally washed away quite easily, and in the rainforest, it's always flooding. So it's always being eroded and washed off. The plants that grow in the rainforest get their nutrients directly out of the floodwater. Okay? So clay tends to be lighter brown, in some places even red, okay, bright red almost. Okay? PEI has really red dirt. If you've ever been to Prince Edward Island, okay, you can get one of those PEI dirt shirts that they stain with the dirt, and they're kind of a reddish brown. Okay? All right, so little to no organic material. There might be chunks of half decomposed rock, weathered rock in there, okay, but it's almost entirely clay. All right, and then below that is the sea horizon. Okay, this is actually a soil horizon picture from around here, just out in the foothills out here. Okay, now you can see the grass is growing here, okay, pretty healthy A horizon, probably down to, I'd say, maybe about here, okay, your B horizon. Okay, it's kind of like this, and then you can see mostly rock. Are there chunks of rock in the other layers? Absolutely, and there's always going to be, right? But the bulk of the rock that's cemented together will be further down. Okay, in some places the bedrock is like a solid sheet of rock. Okay, if you go like towards Ontario and you get into the Canadian Shield, okay, it is literally an entire shield of like granite. It's just solid. Okay, but around here, sandstone's, well, weak. It's easily broken, okay? And so you often don't see just a big plate of it, okay? You see broken chunks of it everywhere. Okay, so the sea horizon is rock. Okay? Parent material varies from place to place. All right, so let's talk solar energy here. Okay, so the Earth's a system, energy comes in, energy goes out. We've kind of talked about that already. Okay, energy comes in through absorption and conversion. The water cycle plays a role there. Some of it gets trapped and transported as latent heat. Okay. Okay, and we already said that too. The sun is the main source of energy. Skip that. Okay. The three methods of heat transfer. We haven't got to this yet. Okay, this is the conduction, convection, and radiation. Okay, so conduction is energy transfer through solid materials only. Okay, so if heat is going to be moved by conduction, it's going to have to do that through a solid. Conduction doesn't happen in liquids or gases. Okay? Conduction is heat transfer by particle collisions. So particles physically run into each other and transfer their kinetic thermal energy to each other, okay, slowly through, okay, the solid material. Some materials conduct heat better than others. Okay? Metals are typically pretty good conductors of heat. That's why we make pots and pans out of them. Okay? One of the best conductors of heat is copper. Okay? Sometimes you can buy pots and pans that have a lot of copper alloy in them because copper conducts the heat through very easily and into your food. That makes them the most efficient kind of pot or pan to cook with. Okay? If you have a cast iron pan, okay, those don't conduct heat as well as copper, but they're pretty good. Okay? Other materials, not so much. Okay? You wouldn't want to build a pot or pan out of something that is an insulator, that is, doesn't conduct heat very well, because then it wouldn't cook it. Okay, so conduction happens, okay, slowly by molecular or particle collision through a material. So if you were making soup and you had to boil it and stir it for a long time, would you use a wooden spoon or a metal spoon? Why would you use a wooden spoon? Yeah, the heat doesn't conduct through wood. Okay, wood is a terrible conductor of heat. That's why a wooden spoon is better. If you use a metal spoon, what's going to happen is the particles on the spoon end, okay, the scooping end, are going to be in the liquid, and they're going to heat up, and they're going to move faster. And once they start moving faster, they start to run into each other more often. Okay, that gets transferred up the handle of the spoon to your hand pretty quickly because metals are a good conductor of heat generally. Okay, so inside the spoon, if you could see the particles, it would look kind of like a mosh pit. Okay, if you've ever seen it in a mosh pit. Okay, you know, the people are jumping up and down, they're running into each other. Okay, that if you run into one person, you knock them off balance. Okay, they stumble a little bit, they hit the next person, but as those collisions happen, pretty soon the energy of that collision is gone, right? It's not a domino effect, okay, but it's transferred a little bit and everybody's just a little bit off balance. But if you continue to heat the middle, okay, they'll get moving so fast that pretty soon everybody is going to be falling down, okay, because of the amount of collisions that would be going on. Okay, so that's kind of how conduction works. You actually have to physically run into each other, okay, to transfer that energy. But the more you're moving, the more often you collide with other particles. They get moving more and more, and they conduct up the material. Okay, everybody with me there? Conduction is not a major form of energy transfer on a global scale. Okay, it is a pretty major method of heat transfer on a small scale, okay, but not on a large scale. Okay, convection. This one is probably the most important of the energy transfer methods because it happens in fluids, like gases, like the atmosphere. Okay, so convection, it works on a small scale and it works exceptionally well on a global scale. Okay, this is how weather happens. Okay, convection is the moving of air, right, James? Okay, in the atmosphere, it's moving because of changes in temperature, okay, and things like that. Okay, how many of you have a convection oven? Okay, or don't know? Okay, so in a convection oven, okay, old ovens just had a heating element at the bottom. Okay, it would heat up and it would heat up the oven. But what happened was the top of the oven would be the hottest because hot air rises. Okay, and so if you were trying to cook two things on different trays in the oven, what was on the top would burn and what was on the bottom wouldn't, okay, because the top would be hotter. In a convection oven, there's a fan, okay, that circulates the air and makes all parts of the oven heat evenly, okay, and that allows you to cook things on the top tray and the bottom tray in the same way, okay. This is how we heat our homes, okay. Think about this. Where are the heating grids in your house? Floor or ceiling? Floor. Why are they there? Because heat rises. Yeah, it makes tons of sense to put the grates on the floor in terms of energy. It makes no sense to put them on the floor in terms of you step on them, break the thing, and fall into it. Not that that's ever happened to me. Okay, but it would make way more sense from a, like, I can walk around on my floor and not have holes in it, okay, put them on the ceiling. But they wouldn't be efficient on the ceiling because hot air rises. Okay, if you put the heat on the ceiling, incidentally, that's how it works in this room. Okay, why this room doesn't work. Okay, the heating elements are in the ceiling. Okay, that doesn't help heat down here. Okay, we want the heat to rise, so we naturally use that convection. The coldest air is near the floor because cold air settles. Okay, hot air rises, so you put the heating vents near the floor, and that hot air coming from the furnace is encountering the coldest air first. Okay, and it'll allow it to circulate. Okay, it's great for heating to have them on the floor. How many people have air conditioning? Having the vents on the floor when your air conditioner is running is about the worst place for them to be. Because they're blowing cold air now. Where does the cold air go? Down, it just sits there near the floor. Okay, we just don't generally have two sets of ducts in our house, okay, to make that kind of stuff work. Okay, but it's good. We do have to heat most of the year, so it makes sense for our heating to be on the floor. If you have hot water heating, okay, so like maybe in your basement you have hot water pipes that run through the slab of your floor, okay, same idea. Heat up the floor. The heat's naturally going to rise. Okay, we want to harness that stuff because it makes the heating more efficient. All of that is convection. Hot air rises, cool air descends. That's convection. Okay, that works on a global scale. okay? The equator is the hottest, okay? Air rises at the equator, cool air comes in from the north to replace it, and that hot air moves north at a high altitude, okay? And all of that just circulates, okay? And transfers energy on a global scale. So convection, super important. Okay, and the last one is radiation. That's any energy transfer by waves. It's how the energy gets to Earth. It's the only way it can travel through the vacuum of space, is by heat waves. Okay? You can feel radiation. Okay, not the kind that turns you into the Hulk, I mean like heat radiation. Okay? You can feel that. Okay? If you've ever stood next to a campfire, you're feeling radiant energy. If you have a radiant heater, like an electric heater at home, okay, the heat that's coming off of that is radiant heat. It's coming off of it as heat waves, and you can feel it. Okay? Everyone follow me there? So for radiant energy, that's affected by albedo. Right? If you want to absorb a lot of radiant energy, you want to be dark in color. If you want to reflect it, you want to be light in color. Okay. Making sense? All right. One of the things that you'll be asked to do with these three methods of heat transfer is demonstrate your understanding of how they work, to use them, or to stop them. Okay? So, as an example, okay, I've got my coffee cup here. Okay? It's relatively well insulated. Okay? Keeps my coffee warm for a fair amount of time because what's inside of it? Yeah, well, it's made of metal. Yeah. What's between? There's actually 2 layers of metal, and there's a gap in between. What's in there? Absolutely nothing. It's a vacuum. Okay? When they make insulated mugs like these, what they do is they vacuum out every little tiny bit of air and then seal it. Okay? Because if there's no air, can you get molecules making a convection current? There's nothing to rise or fall, is there? And if there's a vacuum, conduction can't occur either, can it? Because there's nothing to transfer the heat by particle collision. A vacuum is a great way to insulate things. Where do you suppose this coffee cup loses the most energy? Top. It's just plastic. Okay, like Yeti brags about what great cups they have. Actually, my thermos cup is much better, not a plug. Okay, but it's way better because the lid is actually also designed that way. Okay, on this one, the parts that are hot, always right here, where the 2 pieces of metal, the inside piece and the outside piece, connect. Okay, there's a lot of conduction that happens right there because they're actually in contact with each other. There's no vacuum layer there. And this clear plastic lid, that allows radiant energy out, right? It's transparent. The radiant energy can just go through it. There's no insulation there, so there can be convection. I can feel the heat actually right now with my hands over top of it. Okay, so if I wanted to do a better job of trapping that heat, what should I do with this lid? How could I redesign the lid to be better? How could I keep the radiant energy in? If it's coming by waves, I would want to reflect those waves, right? I showed you the tin foil yesterday, right? The whole inside of this is polished, okay? So there's gonna be a reflection there. Could I make the plastic, instead of transparent, be white? Would that reflect some of that radiant energy back into the coffee? Okay? If you ever open up a cooler, you ever seen a dark colored cooler on the inside? Coolers are always white on the inside, okay? It's so you can tell when they're dirty and you know what parts to clean, okay? But also, it reflects, okay? It's gonna keep energy from the outside from coming in. It's gonna reflect it away. Now, in a cooler, what do they fill the inside of a cooler with? It's definitely not a vacuum. What were you thinking? You might be right. Insulation. Yeah, absolutely. Okay, are there lots of different kinds of insulation? Right, there's the fiberglass stuff, like the pink stuff, right, or yellow, and it's all the little glass threads and fibers. Okay, there's also styrofoam. Okay, have you ever seen that blow stuff that they just spray it in and it just expands and it fills up the space? Okay, all of that insulation works to prevent convection. If air is allowed to move, it will. But inside the walls of your house, you would have insulation. Okay, so let's say here's two different walls. Okay, so this is inside. Okay, outside, outside. Okay, if I don't put anything in the wall, okay, it's just hollow. There's going to be air in there. Would you agree? Okay. Inside my house is hot. Outside my house is cold. Okay. Well, this side of the wall is going to get heat from inside, and the air against this wall will rise, and cold air from here will move in to replace it, and that will continue to cycle, and it will transfer the heat from inside my house to outside. Okay, by convection. If I allow the air inside of there to move, it will, and it'll take the heat with it. Our houses aren't built like that. Okay, they're filled with either fiberglass or styrofoam. What's trapped in between all the glass fibers? Air. But it's trapped. It can't move because it's in between all of these fibers or in little bubbles inside the styrofoam. It can't move. Okay? Does that prevent convection? All you have to do to prevent convection is keep the air from moving. That's all insulation does. It traps the air so it can't circulate. Okay? Now, modern houses, if we want to be like really, really efficient, will also have a layer of foil and a layer of foil. What does the foil do? It prevents radiation. It reflects the heat away. Okay? If we're talking about this layer, it's going to reflect it back into the house. Okay? If we're talking about this layer, it's probably set to keep heat out. Okay? So that your house stays cooler in the winter or in the summer. Okay? Everyone kind of follow me there? That's what you're going to be asked to do. Okay? Apply what you know of heat transfer, conduction, convection, and radiation to a practical situation. Does insulation also prevent conduction? It does, because trapped in between all the fibers is air, and conduction can't occur through a liquid. It can only occur through solids. Okay? Next winter, on a really cold day, okay, run your hand along your wall, an exterior wall. You'll be able to find where all the studs are. It's going to be a human stud finder. Okay? Run your hand along the wall. You'll feel cold spots about every 2 feet. Because that's where a stud is. And the stud is a solid material connecting the inside of the house to the outside of the house. Okay? And heat will conduct through that, and they will feel cold to the touch. It's got to be really cold outside for that to work, okay? But it can work. All right? Making some sense there? Okay? So you got to find a way to prevent conduction, convection, radiation, or conversely, harness them. If I wanted something to heat up fast, I'd basically do the opposite. Okay? I'd make it dark in color. I'd find a way for it to transfer energy by convection to the inside. Okay? All of those kind of things. Has anyone ever built a Quincy? A Quincy is an emergency snow shelter. You basically make a pile of snow and then you hollow it out. Okay? Not an igloo, that's made out of bricks. Okay? But a Quincy, just make a pile of snow, hollow it out. Okay? Crawl inside, and you'll be able to get it above freezing inside there. Why? First off, what color is snow? High albedo, reflects your radiant energy back to you. Okay? Now, snow is an excellent insulator. Why? When the snowflakes fall together, they're all jagged edged, right? There's no two snowflakes alike, right? They all got patterns, they interlock. What happens to the spaces between them? They're full of air. Can that air move? Snow is an excellent insulator because it traps the air and doesn't allow convection to occur. Okay? Snow, okay, this is how animals survive the winter, right? They make a burrow underneath the snow. The snow is a great insulator. Okay? They stay warm. These are the kinds of things you'd be asked to apply, okay? In the guise of conduction, convection, radiation. Okay? Okay, so we did talk about this slide a little bit already in terms of the water cycle. Okay, so hydrologic transfers are energy transferring through the water on Earth. Okay, that's basically through the water cycle, through melting and freezing, evaporation, condensation. Okay, we don't see sublimation and deposition very often, okay, but we do once in a while. Okay, usually a couple times per winter we get a hoarfrost. Okay, where you see the trees all covered in the white frost. Okay, that's actually this process, deposition. The water vapor in the air has gone directly to a solid and frozen onto the trees. Okay, so energy is transferred through the hydrologic or through the hydrosphere by the water cycle. Okay, and then obviously with land, we're talking about albedo and conversion. Plants are carrying out photosynthesis, using nutrients in the soil. Okay, that's the role of the lithosphere. Okay, so make sure, guys, that you write down these 3 fates of solar energy. Okay, I'll scroll up in a minute here, but let's hopefully get those written down before the bell goes. I think the bell's going to go in 5 minutes or so. Is everyone done with reflection? Can I scroll up enough? Okay, when you got that copy down, we're done for today. Tomorrow we'll talk specifically about convection when we talk about global wind patterns.